Welcome to this tutorial on writing mathematical expressions in LATEX. I am Kishore Datta from Handicrafts College, Guwahati. In this session, we will explore how to create clean, precise and professional mathematical expressions in LATEX, whether for academic papers, presentations or reports. This tutorial demonstrates how to understand the basics of writing mathematical expressions using LATEX syntax, differentiate between inline and display math modes and apply them appropriately, how to write and format complex equations using environments like equation, align and gather available in LATEX, how to use a wide range of mathematical symbols and operators in LATEX, how to apply proper equation numbering and cross numbering within documents, and how to develop proficiency with packages like AMS Math and AMS Sim for advanced formatting. To get started, ensure your systems meets the following requirements: a laptop or desktop computer, an operating system such as Windows, Linux or Mac OS, a LATEX distribution like MicTeX, TeXLive or MacTeX, an editor such as TeXshop, TeXworks, TeXstudio or TeXmaker. As I am using Mac OS, the examples will be demonstrated on this platform for ease of understanding. Let us proceed. Before we begin, here are the prerequisites for this session: prior tutorials on LATEX for foundational knowledge, familiarity with text editors to navigate and edit efficiently, basic command line uses for running LATEX commands where needed, a general understanding of mathematical symbols, expressions and equations, and for further reference, tutorials or manuals are available at the following link. LATEX has two primary modes for math: inline math for compact equations within text and display math for standalone centered equations. Inline math uses dollar within dollar environment or parenthesis, while display math can use either double dollar or third bracket. Let's see how it works. Let me write a mathematical description here. The Pythagorean theorem is mathematically expressed as a square plus b square equal to c square, where a and b are the lengths of the two shorter sides of a right angled triangle and c is the length of the hypotenuse. I am using here inline math mode, dollar within dollar. If I use first bracket, we will get the same results as shown here. Let's proceed for display math mode. I want to display the above equation keeping the same contents. For this, I shall use double dollar or slash third bracket environment as shown here. The Pythagorean theorem is mathematically expressed as, now the equation is displayed in a center line. As we see in the output, the equation is now displayed in a single line. Now I want to put a number in the equation. This can be done by using equation environment available in LATEX. Let me show this here. I am writing the equation within equation environment. This shows the equation with a number a square plus b square equal to c square. So there is a number here, number 1. So this is the equation number generated by equation environment. When multiple equations need to be aligned for clarity, the align environment is employed. This environment allows equations to be aligned at a specific symbol, such as an equal sign, enhancing readability. Here is an example where I want to align two equations at equal signs. I shall write the equations as follows: slash begin align and then slash end align. Within this align environment, I am writing a plus b ampersand equal c, then new line, and then the second equation d plus e ampersand equal f. So this creates two equations with number a plus b equal to c, d plus c equal to f. The equation a plus b equal to c is numbered as 2 and d plus c equal to f is numbered as 3. And there is an alignment with equal sign because I am using ampersand here. The Gedder environment in LaTeX is part of the AMSmath package and is used to display multiple equations or expressions in a vertically aligned format. It's centered on its own line. It is particularly useful when you want equations to appear one below the other without any alignment constraints. Here is an example where I want to align the three equations at equal signs. I shall write the equations as follows: begin Gedder and then end Gedder. Within begin Gedder and end Gedder, I am writing now three equations. The first one is, let's say, E equal to mc square, and then new line, another equation, f equal to ma, again new line, and then the last equation, let's say simple equation a equal to b plus c. These three equations, aligned equations with equation numbers. Let's see how equation numbers can be customized using the tag command within the equation or aligned environments. This is useful when a specific numbering scheme is required. Here I am writing an example within begin align and end align. The equation E equal to mc square is tagged as 2.1 and the equation E equal to h new is tagged as 2.2 using tag command. This generates the output as shown here. So there are two equations and the equations are numbered as 2.1 and 2.2, which was given in the tag command. I will now show some basic mathematical symbols. As I have shown before, superscripts can be written as x caret 2 or x caret within second bracket a plus b. For example, I am writing here the mass energy relation is given by E equal to mc caret 2. So this will display E equal to mc square. Superscripts can be written as x underscore 2 or x underscore a plus b. For example, the complex numbers are given by z underscore 1 equal to r underscore 1 e to power I theta 1 comma quad, then z underscore 2 equal to r underscore 2 e to power I theta 2. I am using here quad command to create a space equivalent to the width of the letter m in current font size. I can also use q quad that provides twice the width of quad. Now displays z1 equal to r1 e to the power I theta 1 comma and then a space z2 equal to r2 e to power I theta 2. Fractions can be written as slash frac and then there are two fields, one for numerator and another for denominator. For example, slash frac z underscore 1 then z underscore 2 equal to slash frac r1 r2 and then e to power I theta 1 minus theta 2. So this will display z1 by z2 equal to r1 by r2 e to power I theta 1 minus theta 2. Let's continue with slash sine 60 caret slash arc equal to slash frac slash sqrt3 2. So this produces sine 60 degree equal to root 3 by 2. So for square root we are using slash sqrt and for degree symbol slash sarc, and trigonometric functions are written as slash sine, slash cos, slash tan, etc. I am now writing Greek symbols as slash alpha, slash beta, slash gamma, slash delta, slash theta, slash phi, slash psi, slash pi, and slash sigma. This generates the small Greek letters alpha, beta, gamma, delta, theta, phi, psi, pi, and sigma. The capital Greek letters are written in a similar fashion, but the first letter should be capitalized, such as slash capital G, gamma, slash capital D, delta, slash capital T, theta, slash capital P phi slash capital P psi slash capital P pi and slash capital S sigma, which generates all the capital Greek letters as shown here. Let's continue with summation symbol. Summation symbol can be generated using slash sum. For example, I am writing here e to power x equal to slash sum underscore n equal to 0 caret infinity frac x to power n and then factorial n. So this will display the equation e to power x equal to sum over n equal to 0 to infinity x to power n by factorial n. So here I am using, to generate the sum, I am using slash sum, and limits can be given as well. Further, the limit can be written as slash frac df dx equal to slash lim underscore h slash 2 0 slash frac f of x plus h minus f of x h. So this produces the famous expression df by dx equal to limit h goes to 0 f of x plus h minus f of x divided by h. So here we are using, for limit we are using slash lim. A simple integration is written as slash int. For example, if I write f of a equal to slash int slash frac f of z by z minus a and dz, it displays f of a equal to integration over f of z by z minus a with respect to z. I can put the limits as int underscore a caret b and then the same expression. This yields the limit, lower limit a, upper limit b in the integration. Let's move further to understand how symbols and operators are written in LaTeX. Let's begin with the arithmetic operators such as dot and cross products of vector analysis. The dot product between two vectors is written as slash vac for vector, a slash c dot to represent the dot slash vac b, or I can use slash matbf a slash c dot slash matbf b as shown in the output. The cross product between two vectors is written as slash vac a slash times to represent cross product vac b, or slash matbf a slash times slash matbf b. This generates the output a cross b or a cross b in mat bold phase. Now let's look at the relational operators. They are not equal, less, greater, less equal, greater equal, approx, sim and equivalent. They are written as a slash neq b, then I am using a space quad, a less b, quad a greater than b, quad a less equal b, quad a greater equal b, quad a approx b, quad a sim b, quad a equiv for equivalent b. So this creates the entire output: a not equal to b, a less than b, a greater than b, a less equal b, a greater equal b, a is approximately equal to b, a is similar to b, and a is equivalent to b. Let me write now binary logical operators. Conjunction or AND can be written as slash LAND. Disjunction or can be written as slash L or. Exclusion or XOR can be written as /O plus. Logical NOT is written as /NEG. Implications, that means if then, can be written as /implies. And biconditional, that is if and only if, is written as /IFF. Let me show you the universal quantifiers. There are many universal quantifiers, but the important ones are for all. I can write /for all. Then there exists /exists. Let me conclude by highlighting how LATEX is useful in mathematical typesetting. This tutorial covered the basic of writing mathematical expressions in LATEX, covered the key concepts of inline math mode, display math mode, and the most commonly used mathematical symbols and operators, learned how to adjust the appearance of equations with different symbols and formatting. Brief introduction has been given to more complex environments such as align, gather, and matrix formatting. Thank you.